Thank you, everyone. And I want to start by thanking Tomo and the organizers for the invitation to come here. It's really a pleasure. And I'm enjoying very much the conference, so I'm looking forward to the rest of the talks. So I want to tell you about our recent experiments about graphene superconductivity. Sorry, I think someone took, yeah, this is here, sorry. Yeah, now I'm good. So I want to tell you about our experiments on magic angle graphene superlattices. So just to, to remind everybody, although everybody here knows, just what are metals, insulators, and what are other exotic things. So within a single particle band theory, if your density of states, versus energy looks like this, you have a band which is completely occupied with electrons, then a gap, and a completely empty band. This is an insulator, okay, or a semiconductor. This is the band gap of this insulator. Now, if one of these bands, if you have a material where this band is partly occupied, okay, from energy is here, your electrons have infinitesimally, you have electronic states at infinitesimally low energy available to conduct, and you have a metal. Okay? Now, sometimes you have a situation where your band is, let's say, half occupied, like it is here, so it should be a metal, but however, you do not have a metal, you have an insulator. These are correlated insulators. Okay? You can have, for example, due to interactions, a gap opens so that you go to a situation very similar to this, except that this gap is created by correlations in your system. Yeah? So this is a correlated insulator. Now, there are many examples of correlated insulators. One of the most famous is the MOT insulator, which is the parent compound of high TC couplet superconductors. Okay? So in that case, in the case of the copper, oxide superconductors, you have this, lattice where you have, half filled, the electrons on the copper sides, and then as you remove or add electrons, or as you dope with holes, your system, or you remove holes, you can actually play an interesting game where, now your system has to find this, there is this competition between your electrons being allowed to hop on the empty sides, but not being able or paying a price to hop on doubly occupied sides. Okay? So this thing, is usually referred to as the Hubbard model, which is believed to, represent, the physics of the couplet superconductor systems and lead to this phase diagram. Okay? Now this, we don't know how to solve analytically this Hubbard model because it's not possible. So for about 30 years, people have been looking at different ways in which we can try to, gain some insight into this very exotic, phase diagram where you have many different phases and few of which are completely understood. Yeah? Now, because we don't know how to solve this analytically, and people have been trying to, new approaches in order to try to understand, and not just for the system, but in general, to solve the problem of correlated electrons in physics. And one of the approaches which has gained, the most, momentum and importance is that of using ultra-cold atom lattices. Okay? So, for example, already, about 16 years ago, people were able to realize a superfluid to MOT-insulated transition when you load atoms in a periodic potential. Okay? This was in the case of bosonic atoms, so they were able to realize the Bose-Hubbard model. A few years later, they were able to put fermionic atoms in their optical lattices, so they realized the Fermi-Hubbard model. And the state of the art, the most recent thing that they've been able to achieve is actually antiferromagnetism in the Fermi-Hubbard model. Okay? So they are essentially starting to explore from this corner down into this corner. Now they would like to explore the entire phase diagram with these ultra-cold atoms, but it's very hard because they need to cool down very significantly in order to realize, for example, D-wave superfluidity. So you have these, platforms to study strongly correlated physics. You have actual, quantum materials where you have lattice scales of an order of an angstrom or a few angstroms, and typical energy scales of order, between 100 Kelvin and 10,000 Kelvin, depending what you're looking at. Then you have ultra-cold atoms where the lattice scale is typically a micron. The separation between those atoms is a micron, and typical energy scales are a nanokelvin or hundreds of picokelvin. And what I want to tell you about today is about these magic angle graphene superlattices where the typical lattice scale is of order 10 nanometers, and energy scales are also intermediate between these two strings of order a Kelvin. So this is what I want to tell you about today. I want to tell you about a little bit about this Legoland and magic angle graphene and these 2D materials, and thanks to the nice introduction by Professor Iwasa, this will go fast. Then I'll tell you a little bit about correlated insulated behavior that occurs in these materials that have filling. An unexpected surprise, which by now it's not unexpected, is superconductivity, but it was certainly a surprise for us, and a little bit about the outlook. So, one of the things that people have discussed in the recent past most about 2D materials is the fact that you can stack them arbitrarily on top of each other. And people, my colleagues have these review papers where they make analogies with Lego sets, where you can just put Lego pieces on top of each other at will. And that's, I think, one of the key defining characteristics of van der Waals heterostructures. Now, for all of you that have played with Lego, and I have small kids, so I've played Lego with them, sometimes kids have trouble stacking the Lego pieces on top of each other because you have to align them perfectly in order to stack them on top of each other, okay? So this is something which you can do with 2D materials, but in my opinion, this aspect of 2D materials is not perhaps the most defining or the most unique. After all, you can also grow by MBE semiconductor heterostructures, which make a little bit, like Lego-like thing. Perhaps one of the most defining aspects of van der Waals heterostructures is the fact that you can actually stack the 2D materials on top of each other with an arbitrary angle between the two crystalline lattices. This is something which is completely unique and unprecedented. You cannot do that with MBE-grown semiconductor heterostructures. You cannot do this with bulk crystal growth techniques. Only with 2D materials, you can choose two materials and put them with an arbitrary angle of rotation on top of each other at will, okay, that you choose. And it can be any angle. You're not constrained by lattice mismatch, chemistry, anything, okay? So this is something that, is quite unique to van der Waals heterostructures. Some people call it twistronics. And, let me stop there before you get sick and show you a little bit about. So let's go to the system of graphene on top of graphene. Okay, so I think most of you are familiar with graphene. Graphene has this electronic band structure where you have at low energies Dirac cones, linear energy momentum dispersions. This is the Brillouin zone. It's hexagonal, and you have the K and the K prime points. Okay, so you have 4 degrees of freedom in graphene. You have electrons have spin up, spin down, and also valley K prime. Remember this. Now, what happens if you put a graphene sheet on top of another graphene sheet? Okay, then you have this. Now, let's look at what happens if you rotate those two graphene sheets. In real space, what happens is what you saw before. You form a moire pattern, okay, with a wavelength that depends on the rotation angle between these two crystalline lattices. In reciprocal space, when you rotate the real space lattices, your reciprocal spaces also rotate, okay, and by the same angle. Okay? This means that your Dirac cones separate in momentum space. They separate by a momentum which is proportional to the sine of the rotation angle. Okay? So this twisting leads to layered Dirac cones which are separated in momentum space. Now, starting from a finite rotation angle, let's go towards smaller and smaller rotation angle, and let's see what happens to the electronic structure. So delta K here, the separation in momentum goes as K sine theta halves. For small theta, this goes as theta. So if we start from a small angle, but not very, very small, just small, okay? This is the situation that you have. Okay? You have these Dirac cones. Now, this situation is the situation that occurs if these two graphene sheets would not talk to each other. Okay? So these Dirac cones would interpenetrate each other. Now, if this, in real life, however, these two graphene sheets which are on top of each other, they're just 3 angstroms apart, and the electrons in one layer see very much the electrons in the other layer. Okay? So what happens in reality is the following. There is some interlayer coupling, W, and this opens up a gap here. Okay? There is band repulsion at that crossing point, and it opens a gap there. This is the situation when the rotation angle is still large, such that this interlayer coupling is still smaller than the location of that crossing point in energy. Now, if I now decrease the twist angle, these two Dirac cones are going to get closer and closer, and at some point, this interlayer coupling becomes of the same order as that energy point there, the crossing point. So you realize, this band which is being pushed down by the level repulsion actually gets pushed down all the way to 0 and becomes a flat band. Okay? So this occurs for when the interlayer coupling is about BFK theta. Okay? And this flat band condition is reached at the so-called magic angle. Okay, this magic angle term was coined by Bistritzer and McDonald, and they calculated that that magic angle for the case of bilayer, graphene on top of graphene would be 1.1 degrees. There was some earlier calculation and also some experiments showing that at this angle, something interesting would happen. Okay? Now, this was sort of a cartoon. Let me show you an actual calculation of how this happens. So, again, we have here the two rotated graphene reciprocal spaces for the graphene sheets. You can form a superlattice Brillouin zone, okay? As you can see, because the real space superlattice is very large, okay? Because you have a long Moiré wavelength, your superlattice Brillouin zone is much smaller than your individual graphene sheets Brillouin zones. And I'm going to show you now a video of what happens with the electronic structure. This is for rotation angle 3 degrees. Within this energy window, this just looks like graphene, Dirac cones, okay? 6 Dirac cones coming out of the K and K prime points, and they're reciprocal, The first thing that you're going to see is that as I rotate the angle towards smaller angles, because my real space lattice is going to get longer, that means that my Brillouin zone is going, superlattice Brillouin zone is going to get smaller, okay? And then you will see also the evolution. So let me run this video. So you see I'm rotating towards smaller and smaller angle, and a band is appearing now, which is becoming flatter and flatter, and at 1.1 this thing is going to become very flat. Okay? So you see it's becoming flatter and flatter. At 1.1 degree this becomes a flat pancake there. As you keep rotating, something interesting also happens. Okay? Now because my student spent a lot of time making this video, let me run it again. Okay, so you can appreciate it. So as you can see, something happens as you go towards very small angle, and at a special angle, this band becomes very flat. Okay? That is at 1.1, a flat pancake, okay? And then it continues evolving. So this magic angle at 1.1 degree is when you have that flat band. So you can see here a cut of that flat band. Okay? Actually, by now these calculations are a little bit old. They're better calculations nowadays. Okay? But you can see that these blue bands are the flat bands. Their bandwidth, okay, is not completely flat. It has a little bit of dispersion. Okay? But the bandwidth is orders of magnitude smaller than the original graphene bandwidth. Okay? The Fermi velocity gets renormalized down by many orders of magnitude. So now, flat band, okay, flat in momentum space means localized in real space. Okay, you just do the Fourier transform. So what happens is that if you calculate the density of states in these flat bands, okay, as a function of space, what you have is these localized peaks at regions where you have AA stacking, where the two graphene sheets are locally, approximately exactly on top of each other, and these regions of AA stacking are separated by AB and BA, stacking regions. Okay, so you have now a situation which schematically is like this. You have AA regions where there's a high density of states and your electrons like to be, weakly tunnel coupled through AB and BA regions. Okay? So this forms now our triangular, in quotes, in reality is a honeycomb, Fermi-Hubbard lattice for your electrons. Okay? So let me show you then what we have measured. Now before let me show you data, let me tell you how we fabricate our devices. So we take a glass slide with a polymer stack, and then we take a substrate which has hexagonal boron nitride, about 10 nanometers thick. This is a nice dielectric. We pick it up. Okay? Now we bring another substrate which has monolayer graphene on it. This is standard by now. And then we position our substrate such that we pick up half of the graphene. Okay, we tear it and we pick up half of the graphene. Okay? If you look from the top, this looks like this. Okay, we have the hexagonal boron nitride, the graphene piece, and the overlap between the two regions now is stuck to the hexagonal boron nitride. Now these two pieces, because they come from the same crystal, they are crystallographically aligned. So now we can rotate the substrate or the slide by any angle that we want. Okay, and we have very high precision on doing this. Then we overlap them on top, and then we stack them. So that's how we form a heterostructure with a given angle with a precision of about 0.1 degrees. Then we pick it up, and then we can continue the fabrication of our devices. Okay? So in the end, you have a device which looks like this. You have this twisted bilayer graphene. It's doubly encapsulated in hexagonal boronitride, and we have a local gate. We can also have a top gate, and we have source and drain contacts, and we can perform, standard transport experiments as a function of gate voltage, which controls the Fermi level. So let me tell you how conduction through just monolayer graphene looks like, okay? Just regular graphene. If you measure the conductivity versus density, if your Fermi energy is deep in the valence band, you have lots of holes, you conduct very well. If your Fermi energy is deep in the conduction band, you have lots of electrons, it conducts very well. If your Fermi energy is at charge neutrality, you don't have charge carriers, so you conduct poorly. So you have a V-shaped conductivity of graphene, okay, versus density. Now let's look what happens when we have this type of heterostructures. So I'm going to plot here conductivity versus density, and I'm normalizing the density by the total amount of charge of electrons that you can put on those flat bands, okay? Which is actually 4 electrons per Moiré unit cell. So this means 4 electrons, 4 holes per Moiré unit cell. For devices with large twist angle, the conductivity is just V-shaped, same as graphene, okay? Let's now choose a device which has a small twist angle, but not yet the magic angle, okay? So let's choose 1.8 degrees. So at 1.8 degrees, near charge neutrality, you have V-shape, like graphene. But now, when you fill completely the conduction band, you have an insulated state. When you empty completely the valence band, you have an insulated state. This is just because as you go from one band to the next, you go through a gap, so you go through an insulated state, okay? So these gaps which occur at full filling of your Moiré unit cell, those are single particle in origin, okay? Although correlations affect them, they are single particle in origin. So these gaps have been seen, we reported them a couple of years ago and have been seen by several other people by now. Now let's choose now a device which has, twist angle at the magic angle, very close to the magic angle, 1.08 degrees. You have V-shape near charge neutrality, same as graphene. You have insulated state at full filling of the superlattice, but then you have 2 new states, insulated states at half filling of your valence band and half filling of your conduction band, okay? So now I'm showing you actual data with units now, conductance versus real gate-induced electron density, okay? So as you can see, V-shape near charge neutrality. From here, we're doping with electrons, overall from charge neutrality. From here, in this direction, we're doping with holes, overall with respect to charge neutrality. You can see these insulated states at half filling. Yeah? So those insulated states, first of all, we only see them if we have devices, and by now we have about 10 devices, which are twisted with a rotation angle of about plus minus 0.1 degrees with respect to 1.1. Yeah? If you are 0.3 degrees away, everything is gone. Okay? So that's the first thing. And then these insulated states at half filling, they exhibit a metal-insulated transition. This is conductance versus 1 over temperature. So this is metallic, and this is insulated. So there's a metal-insulated transition for these insulated states. That's already quite peculiar. We don't see that very often. But the thing that caught our attention the most, the thing that we found most striking is that this insulated state, whether it's for electrons or for holes, disappears in a magnetic field. You have an insulator to metal transition as you apply a magnetic field. This is something which is totally unprecedented in my experience with graphene devices. With graphene devices, if you apply a perpendicular magnetic field, you either go from metal to insulator or from insulator to a stronger insulator. You never go from insulator to metal, okay? And in fact, it doesn't matter if you apply this magnetic field perpendicular to the layers or parallel to the layers. In both cases, you go from an insulator to a metal. So now, the picture that we got after doing plenty of other measurements, and you can look at our paper for more information, is that in a single body picture, you have these 2 bands, okay, which are part of the flat band. In a many body picture, you open a gap due to correlations. This gap is actually made of singlets, and that's why when you apply a magnetic field, in particular a Zeeman field, okay, you polarize these singlets, and you close this gap, and you start conducting, and you go from this insulator to a metal transition. Now, similar mode-like insulator behavior have been observed in ABC trilayer graphene or hexagonal boron nitride by the Feng-Wang group at Berkeley. So this is more general than just graphene on top of graphene. Now, when we look at this thing, this If we look at the temperature dependence near the correlated electron insulator state, the correlated insulator state for electrons, we do temperature dependence, we just see normal behavior for an insulator. At high temperature, higher conductance, so nothing too fancy happening. If we look, however, near the state for correlated holes, what we see is that at half filling, we have typical insulator behavior, but right next to it, we have this big enhancement of the conductance as we decrease the temperature. So that was the first thing that we were like, what's going on here? So these devices were two-terminal devices, which is a measurement geometry which is very much okay to measure insulators. But if we want to measure something that may have very low resistance, you want to change geometry to a four-terminal geometry. So when we saw this data, I told my students, let's fabricate now four-terminal devices to see really how low, how high does this conductance get. Yeah? So we made four-terminal devices. The geometry is very similar to the other one that I told you. It's just that you have hole bars so that you can measure in four-terminal geometry. So this is a device. We first characterized them in two-terminal geometry because it's simpler. So this is a device, with a rotation angle of 1.16 degrees. These data are in the presence of a finite perpendicular magnetic field. And what you can see is similar to before is V-shaped conductivity near charge neutrality. Then we have at full filling an insulating behavior at full filling for electrons, okay? For holes, -4, +4. Then you have features, at +2 and -2. This is half filling. You also see features at +3 and -3. There's a lot of interesting physics that I'm not discussing, and we have a lot more data that I'm showing, okay? But let's concentrate at half filling. If I now remove the magnetic field, okay, what you see is around the correlated electrons, not too much happens, but around the correlated holes, a lot of things happen, okay? So this is actually in a two-terminal geometry. Then we can now, because these samples have actually four terminals, we can do proper four-terminal measurements. And what we see is that this magic angle twisted bilayer graphene superconducts, okay? These are two devices, 1.16 degrees and 1.05 degrees. Our resistance goes down by several orders of magnitude below our measurement floor. This thing superconducts. You can apply finite current bias and measure typical superconducting states. You can apply any test that you want of 2D superconductivity. Because of time, I'm not showing the magnetic field data and so on, but you can look at it in the paper. This clicks every box for two-dimensional superconductivity. And of course, because we have this electrostatic gate, and this is a system which has very low density, we can actually do something like this, okay? So we can park our gate in this region, and we can measure as a function of temperature and gate voltage or gate-induced density, we can measure, this is the correlated insulated state for which you have high resistance, and on both sides you have a superconducting dome and another superconducting dome here, okay? So this is, remember, this is the correlated insulated behavior for holes from charge neutrality with doped graphene with holes, and then around this correlated insulated behavior for holes, if we keep adding holes, we have this big superconducting dome. If we subtract a few holes, the equivalent of electron doping, we have a smaller superconducting dome. Yeah? So this is something which immediately reminded me of the situation that you have in this type of phase diagrams for cuprettes. For cuprettes, people choose hole doping in this direction, electron doping in that direction. Let me just flip it for you so that we are in the same situation. Okay? So as you can see, in cuprettes, there is a multi-insulated state at half filling. You dope with electrons, you have a small superconducting dome. You have dope with holes, you have a bigger superconducting dome. Here we have also a correlated insulator, mod-like in the sense that it's at half filling, okay? If you dope a little bit with electrons, you have a superconducting dome. If you dope with holes, you have a bigger superconducting dome, okay? So the big difference, of course, is that here we can do this in situ, in a single cool down, in one disordered realization, just by tuning a gate voltage. This takes us 30 seconds to sweep with gate voltage. Here, you need different material classes for electrons and holes, and for each point on this axis, you need an actual different crystal growth or MBE growth, okay? So you can see that this presents some advantages because we study, a single system and in situ. So, this is data for another sample, okay? You typically see actually a much stronger asymmetry that I'm showing here. Most of our samples look like this, a much bigger dome for holes than for electrons, okay? And this correlated insulated state competes with superconductivity at the lowest temperatures. By now, we have several other devices. Our maximum TC actually is already about 2.5 Kelvin, and we keep measuring devices. We're starting to map TC at optimal doping versus twist angle, and we see extreme variation as a function of 0.01 degrees rotation angles. So now, how strong a superconductor is magic angle twisted bilayer graphene? So Tomo, made this, very nice connection, and plot, for many materials about TC and TF, okay? Now, this is something where you can see that, most conventional superconductors are sort of in this region. The more you go in this direction towards this blue band, the more unconventional you go typically, okay? So here you have the cuprates, the iron pnictides, the heavy fermions, the organics, okay? Here are the data for ultra-cold atoms multiply both axes by 100 million. So magic angle twisted bilayer graphene happens to be here. It's one of the strongest coupled superconductors that we're aware of. Yeah? And this is tunable, of course. And now, in case you haven't been paying attention to the archive, this is just a list of some of the papers that have appeared in the past 2 months trying to explain this behavior. Okay? There are all kinds of, order parameters and correlated insulator states that people have predicted, and probably by now there are a few extra. I'll be done in a second. So let me just, in the last minute, tell you a little bit about Outlook. So this is, of course, a very tunable platform to study correlated physics. But one thing is, which is important, is that this can work not just with graphene on graphene, but this can work with any 2D material. Okay? We have by now 2D materials that exhibit all of the condensed matter behaviors that you can imagine. Okay? And if you put this material on top of itself, there will be a condition, a magic angle, where either globally in momentum space or locally in momentum space, you will realize these flat bands, and you will bring extra correlations if they weren't. If you will bring correlations if they weren't there, you will bring extra correlations or modify them if they were present. Okay, and we can do this with any 2D materials. And in fact, for many materials which are a little bit correlated, you don't even need to hit the magic angle. You can just be at low twist angle, and you will introduce extra correlations and modify correlations, and people are already starting to predict all of these for all 2D materials, okay? So with this, I want to thank, my graduate student, Joanne Sao, who is mostly responsible for this work, also with close collaboration with Vala Fatemi, and our collaborators at MIT and Harvard. I want to thank you for your attention.
Thank you, Pablo. Yes, question first, Dr. Bianconi. And then many questions, okay, so.
Okay. Thank you for beautiful presentation. It's a beautiful confirmation of my theory.
So many people have told me that.
So your assignment to correlation has nothing to do with the physics you are doing. There is no correlation. You have a pi electrons. You are only modulating the nanoscale geometry of the material. There is nothing in correlation. So this is a game of engineering the band structure with a flat band and this steep band. It's very close to Alex Mueller ideas, because we have a localized state and a very steep band. So it's nothing to do with Anderson idea. So I think all the beautiful words, but all the interpretation is completely wrong. There is no correlation in your system. It's a pi electrons.
Actually, 90% of the theories disagree with you, but it's okay.
Okay, thank you for the discussion.
We have played with graphene, single layer graphene on hexagonal boron nitride, which also introduces, periodicities and so on, and there's no insulated state, no superconductivity. So, and we have a lot of data that I'm not showing, actually showing that the superconductivity is a bit more special than you might even think. So, most likely correlations are extremely important. You will see.
Pablo.
Yes.
So, I'm going to ask a more detailed question. So, when you show these first principle calculations, which I understand are from a few years ago, it seemed that there was almost no gap between the flat bands and the other bands. But in your plot, there seems to be a significant gap that these flat bands are quite separated from the rest of the bands. Do you know how much is the gap that you would assign experimentally? How big is that compared to the bandwidth?
Yeah. So for the full filling, so the single particle gaps, in the experiment, we see them of order 30, 40 millivolts. Okay? The latest calculations, which include relaxation in the X, Y, and Z direction, predict gaps which are of similar magnitude. It comes from part of the relaxation, yes. So Cosino has a paper in 2017 doing XY relaxation where already those gaps are of order 15 millivolts. And if you now include relaxation in this direction, people seem to see bigger gaps.
Yes. So, so have you seen superconductivity in the electron side?
So we've looked and we haven't seen signatures of superconductivity on the electron side yet.
You have any idea about the difference between the hole and the electron?
We're not sure about what's the difference. I mean, the band structure is hugely asymmetric. So from that point of view, there is already an asymmetry between electrons and holes. But we have measured by now 8 devices, and we haven't seen a strong signature of superconductivity. Sometimes we see something, but if it is there, it's way weaker and much less prevalent than for holes, and we're not sure why. Other than the fact that the band structures are quite asymmetric, the valence band is much flatter than the conduction band, for example.
Okay, Imada-san, please.
So actually, I have very quick 3 questions.
Okay.
The first one is, can you detect the Meissner signal in that superconducting state? The second question is, what is the real size, spatial size of the sample? The third question is, would it be possible to detect, if possible, the stripe order if it exists?
Yes. So Meissner effect, we don't have any local probe detecting Meissner effect. I haven't showed magnetic field data because of time, but we have, of course, a lot of magnetic field data that you can look in the paper. There you have some of our magnetic field. This thing has a critical field in plane, which is very large because it's a 2D superconductor. Out of plane, it's smaller, okay? We can extract, superconducting coherence length, everything that you want, so, you can look in the paper. The typical size is about square micron, a micron by a micron. It can be bigger, there's nothing fundamental about it. We just try to make small devices so that they're as uniform as possible, but a square micron. And then, whether we detect, stripes, so I'm not showing data, but we have very strong evidence that the superconducting state is nematic. It exhibits anisotropy in the critical field as a function of direction, and we're now analyzing further those data. And we have very strong evidence that there is something special with anisotropy. It doesn't follow the symmetry of the lattice, actually.
Okay, Keith-san, please. The microphone, is it okay?
So, is there strange metal? So, again, I haven't shown those data. Thank you for asking. I haven't shown those data because of a question of time. But this data is on the paper. We have a lot more data now. I'll show you in a moment. We have indeed a linear resistivity with temperature behavior, okay? And in fact, again, because we have a continuous charge density tuning, we have a lot more data now like this, okay? We can continuously take this, and we're doing an analysis of this Planckian dissipation, and it seems to be there. So I hope to report, in a few months, more detail about that.
Here. Hello? Hello. Here.
Where are you? Oh, sorry.
Yes. So, do you have any experimental knowledge about spin correlations in your parent, so to say, correlated insulator?
We don't. With transport, it's not very easy to measure magnetism with transport. These samples are too small to do squid measurement, big macroscopic squid measurements, something like that. We're going to measure with nanosquid to see if we can detect something, but we haven't done it yet.
Yeah. So can you hear me? So a quick question. You had in the data that you have for the conductivity, there is a very strong asymmetry between the electron and hole doped system.
Yes.
However, the picture that you were trying to present initially was pretty much particle-hole symmetric. So based on the experimental data that you have on that and everything else that you have measured, you gave also a long list of theories that try to explain that. Based on what you have, what theories can be eliminated out?
What theories can, what, sorry?
Right, or give me a physical interpretation of why those things are the way they are in your system.
Sorry. So if the question is, why, which of these theory papers accounts for electron-hole asymmetry with respect to this correlated insulator of holes? Is that the question, or? Okay. Experimentally, I'm showing all the data, okay? No interpretation, no nothing. We have always a much bigger dome for holes than for electrons around the correlated state for holes. We don't know why. These are experimental facts. We see it in every device that we have measured, typically very asymmetric, sometimes a little bit more symmetric, like the one that I showed at the beginning. Theories, again, the list is very long. There are all kinds of states. I remember in particular one theory paper that mentioned that you have different order parameters if you look at the orbitals when you dope with electrons and when you dope with holes. In one case, it goes towards P plus IP. In the other case, D plus ID. And P plus IP is more sensitive to disorder. That's why the dome for electron doping is smaller. Could be. We don't have any evidence yet for that. Okay? But, it's all too new. We don't know yet.
Okay, one last question.
Yes, so given the fact that in order to explain the insulating state, you have to invoke correlations, right? So I think this is pretty clear. But in terms of superconductivity, with such high density of states, almost any interaction would produce a 2 Kelvin superconductivity. So, even electron-phonon interaction. So probably there is a reason why you think superconductivity is unconventional. Can you explain that?
So there are several reasons. One of them, there are very few superconductors which are conventional here, okay? That's one reason. But as you say, if you put infinite density of states, who knows? Maybe electron-phonon does the job, okay? Now, it's not very easy that electron-phonons will give you, I should have started this talk by saying I didn't know anything about correlations 6 months ago, so forgive me, if I say something. But I don't know any vanilla VCS superconductor which appears, when superconductivity appears on both sides of an insulator state. That's another reason. More recent data that we have, as I mentioned before, tells us that the superconductor seems to be nematic also, which again goes kind of against, VCS. So the preponderance of evidence, but of course we don't have ARPES data showing, or we don't know what the order parameter exactly is yet. But the preponderance of evidence, also this strange method linearity behavior, near optimal doping, all these kind of things tells me that this thing is a little bit different. But we need to continue. These are the first experiments.
Okay, thank you very much. So please continue the discussion during the coffee break. Thank you very much.